the Navy before.
Welcome to the review session for the final exam. Yay! And you give yourself a round of applause. We made it this far. As I told my class today, that's right there at the crest of the hill. Just imagine everything's downhill riding the mountain. Smooth sailing. Before you know it, it's going to be the Design Expo, and you're going to be presenting your capstones, and you're going to be making fun of your classmates' capstones. Wow, that's what you did? Sorry. It's fun to make fun of other people. It's wrong, but it's fun. All right, so what do we learn? See, I made a whole different slideshow. It's in my office over there. Didn't do me any good. Not on my thumb drive. Mass moment of inertia we covered since exam 3. Rigid body, Newton's second law, rigid body, work and energy, rigid body, impulse momentum, / impacts on the last day of class. All of this is fair game on an exam. And I'd also mentioned, generally in my class, for the final exam, I ask 4 problems. Usually one of those problems, in addition to what you're seeing here, is a rigid body acceleration problem that involves also finding the velocity. The final exam is 2 hours, and therefore generally, so you'd say 4 problems, 2 hours or thereabouts, a half hour per problem. I usually try to make them an equal amount of difficulty, and for myself, be able to solve it in 15 minutes, the 2-to-1 ratio kind of thing. And that includes not taking shortcuts and trying to hold myself back from being Mr. Speedy Hands and just try to be kind of like, okay, like a student that knows what they're doing and not a professor that already knows how to do the problem kind of. So there we go. Here's our equation sheets, and once again, I should be updating this. This is from spring of 2019, five years old. Okay, so it still has the same mistake here, where I have, when we're doing on this one, the cross product of the momentum crossed with the position vector. That should be the other way around. So that mistake is still there. It's fixed on the equation sheet, just not on this thing right here. All right, so I have a bunch of problems I've uploaded. I think I've given the solutions on both of my class Blackboard and the recitation class Blackboard. Is that true? Anybody testify on the recitation Blackboard? I hit the hidden from students thing and switched that off. I did on the recitation is what I'm asking about. Anybody? Okay, so if you're a recitationist, not in my class, and the solutions are not posted on the recitation Blackboard, please let me know, and I'll make sure that those can turn on. But I will give you the same beating drum, boom, boom, boom. Or there's been so much stuff about pets in the news lately. I don't want to say I don't want to beat a dead horse. So I didn't want to say the bad thing. You shouldn't hurt anybody. You should be just a nice, kind person. But I want to beat the dead horse. The most important aspect about preparing for any exam is that you practice like you're going to play. You have to simulate an exam. You got to try to put a blank piece of paper in front of you. Maybe make some quiet time. Get to tell the Barney student roommates to go away because they don't really, they don't even have exams. I don't know what they just print those degrees. They just give them away. This is recorded, so you can tell them I said that. All right, it's evidence against me. Use it against me. I don't mind. But anyway, you want to practice like you play, get nice and quiet, even time yourself, push yourself. Maybe start off with an easy one if you're not feeling so comfortable. And we're going to go to some must problems here in a second to see things. But here's some old problems from the Coast Guard Academy. These were not final exam problems because they actually had 5 exams and then a final exam. I know it was nuts. I just like to torment those poor kids. Newton's second law. I don't know where this one came from, but this is actually a problem I think I've done in class, or one similar where you got a ball hitting a stick. That's an impact problem for impulse and momentum, very common thing. you got this ball rolling down a hill, so there's a Newton's second law, but you could probably, you want to do the friction? So we can cover any of these problems. We can do take requests of any type that you want as part of this. I don't want to keep just going through slides and describing problems, but I'm riffing right now because I meant to have a plan in place. I don't have a plan in place. So you're going to be my plan. Yes, please.
Is there going to be pulley problems?
I don't think there's going to be any pulley problems. I don't have that planned yet. The problem with trying to make a pulley problem for me, I think I might have one time made a homework with a rigid body thing that was connected to a pulley. It seemed particularly mean because you had to separate the things out. But in order to do a pulley problem with the rigid body, Newton's second law, I have to kind of make it convoluted. Although actually, there are practice problems that involve that.
So it's not going to be on the exam, though?
I don't know if it's going to be on the exam. I'm being dead serious. I'm writing it tomorrow.
Oh, okay.
Yeah. I go through. You don't need to hear. You're probably bored. Already are by this description of how I go about making the exam. But I have a bunch of old exam questions all laid out on this big grid, and I'm looking. Okay, here's what I asked that year. Here's what I asked that year, and sometimes I repeated that one. I repeated that one too often, too soon, and that kind of thing. And then I try to pull some new ones and that kind of stuff. I go through a whole process. It's completely inefficient. Probably one of the most inefficient exam and homework writers here. But I used to get picked on at my old job by my good friend, Dr. Alicia Garcia. If you're listening to her, Alicia. She picked on me because I took forever to write a problem.
Like regarding the Newton's second law problem, are there going to be any that are based on like polar coordinates? And if so, can we do that?
I can't think of one right now, of a way to do that. Because basically what we need to do is, I don't, because we're doing rigid body, because, you know, we haven't, unfortunately, or not fortunately for you, I don't know. I'm just trying to make a measure of you. We haven't tested you on rigid body Newton's second law, so I'm going to test you on rigid body second law. And in order to make a polar coordinates with that would be a little challenging. It makes it complicated. And one of the dangers in writing an exam problem is that nobody in class can understand it if you make it too complicated. Which I've been there. I've done that. Experience what not to do. So any there was a question about the pulley problem, and it suddenly reminded me that this was just various topics, and this was a pulley problem. But this is a particle, rigid body particle thing, so there's not much chance to answer that. But if you were going to ask, one second, this is sort of a pulley problem. So if you mean this, yeah, that would be fair game. So we could do that if you wanted to do it in two separate ways. There was another question. Can we? Oh, absolutely.
After, can we do a moment of inertia?
Oh, sure. Absolutely. Okay. So this might be a little inefficient, but I gotta write some of this down. So maybe you want to write this down as I'm doing it. I'll try to be quick about it so as not to waste your time.
I don't think
Get more problems in. More is better. Not always true, but in this case, maybe. More preparation is better. All right. So this problem can be done in either of two ways. It looks like it's kind of set up for us. It looks more like a Newton's second law problem to me. I'm hearing little dings. Is that me? Any Monty Python fans here? You have to be deep cut and see the movie The Meaning of Life, and they go to a hospital, and there's a machine, and it goes, this is the machine that goes, bing! And my wife and I, 30 years old, we had a pregnant, her not me, and going to Lamaze class, and there's probably 20 couples, and they all seemed older than us, than one couple. We seemed like the youngest people there, and we were already 30. And so the woman brings out a machine to show what the incubator is, and my wife and I both, in stereo, go, bing! And everybody else is, what a bunch of lumps. 20 people never even watching my play. Anyway, okay, so that's not why you're here. So what we have, what's it, 14 kilograms is this thing. I don't know what to call it. I'll just call it MC. MC hammer? That's a really stupid reference. And a centroidal radius of gyration. I guess I'll go with the K thing. I don't really like K, but millimeters. And cylinder A and butt B are attached by cords. They're wrapped around the thing. The coefficient of friction, kinetic coefficient of friction, is going to go mu 0.25, and it's released from rest and determine the velocity of C just as it hits the ground, and that's going to be 900 millimeters. And so let's go with Newton's second law to start with. We're also told that the answer is going to be 2.933 meters per second. And I can see my own handwriting here, so I wrote/modified this problem back in the old Coast Guard days. I wasn't in the Coast Guard, I taught the Coast Guard Academy. I went to the United States Merchant Marine Academy, and we, merchant mariners, hated the Coast Guard Academy. But then I worked there and I found out they were very nice. They were very nice, but it was too nice. Felt kind of awkward. Why would be so nice all the time? I one time got mad and I cursed. In the hallway, thought nobody could hear me. They brought me in and had a counseling session. I had to get an anger like class. Didn't approve of cursing. Felt awkward. All right. Maybe you two are against cursing. All right, so I'm going to get the mass moment of inertia of this thing. They give us a radius of gyration. Anytime they do that, we'd rather we get a little shorthand thing going on here. We go M. I guess I'll write this C. That's because we have there K squared, right? This radius of gyration, and some books use R or RG or some weird damn thing. And K is confusing because K is usually spring constant, but radius of gyration, hopefully, you know, maybe it'd be better if we went RC. I don't know what the thing is RC, because it depends on what your professor uses, what you're used to. So we go 14 times 0.165, right? We don't want to use millimeters in here. That gets confusing because we would like to have the units come out to be kilogram meter squared. And I might, chair's not high enough, chair's not low enough. This is going to look stupid, but I got to do it. Sorry, it looks dumb. I hurt my back like really, really bad several years ago. It would only take me a little while before bending over ever so slightly would put me into nights and nights of pain, and I have to drive to Michigan, so I can't like afford to have my back even when I look like an idiot right now. So this would be kilograms meter squared. Oh boy, this is going to get old soon. All right, so also we have a B right here. I did make it a circle. We need to know the friction here. They gave us the coefficient of friction, so we're going to need to know it. Truth is, we're going to use Newton's second law anyway, so we might as well write the free body diagram and the IBD. I have in the past been fussy that any time that you are doing something with forces, make an FBD. You go, why? Because I've seen people make mistakes by not making the FBD, by taking the shortcut. So even if you're doing a Newton's second law, this is getting old. So that's, maybe this is going to be really weird. How high can we make this chair is the question. That's not bad. That looks a little weird. It's like I'm at the kids' table. All right. I don't mind the kids' table. I'll eat the kids' table. All right. So anyway, even though we're using that Newton's second law, it'd probably be good practice to just draw this FBD part of the thing, and because you weren't doing acceleration, you didn't need it. So let's go Newton's second law first, and pretend, and then do work energy. Not spend too much time, but let's just do it right here. So we're going to go with the FBD, and these are going to be treated like particles. IBD, the little weights. I can't impress upon you the importance of the FBD. I'm not just an obsessive person over the thing. But in terms of an engineer trying to figure shit out, it's one of the most important tools.
Why didn't you join these parts together?
Okay, good, great question. Because there's going to be a reaction force right here. And I'm not going to want to find that reaction force. I think, let me think about it. Yeah, I think it's going to be best to go ahead and not separate it. But I'm actually, thinking out loud in terms of like the forces and the directions. We might be able to do this. I will try it later, but I don't think it's a good idea. It's just a generally good idea to separate this thing out right here. When it comes to Newton's second law, and when you have like this other surface this thing is acting on, I might actually be able to do it. I might. I don't know. Let's go ahead and proceed as I have, but I will concede that it's kind of that is a possible approach to the thing. And actually, I'm not showing my Newton's second law. Bless you.
Thank you. Wow.
So here's F, and by the way, this tension is not the same as that tension. That's a little bit thing to do. So I don't know which one to call it. I'm going to call that FT1. And here we're going to have a weight of this, which is going to be MVG, and an F. There's only one normal force, so I'll just call it Fn. And now it's going to be a friction force, and that's going to be the opposite direction of its motion. And then it's going to be accelerating in that direction. So I can't fit that right up in there, otherwise I would. MBAB. And so let's see, okay, a couple things in here. We go to the sum of the forces in the y direction equals mass times acceleration in the y direction. We can already see that that's going to be 0 in the y direction. Like the only acceleration is in the x direction. So this is the almost trivial mg plus Fn equals 0. So Fn is equal to, I'll go ahead and put numbers in now. So 9 times 9.81, and we get 88.29. And then the friction force is going to be mu k. I guess I should have put k. Times Fn. So 0.2589, 88.29, and I got to fit it underneath there. So 22.07. So we should continue in the x direction. I got some more space over here, so I'm going to do a carriage return and the things that you probably have only heard about, typewriters. We're just having a typewriter discussion today. That's what old people say, stand around and talk about typewriters. I didn't do the right thing by putting him up. I fixed it. All right, so we're going to have a negative FT1, and we're going to have a negative FF. Does that sound right? Yeah, it's resisting motion. Is there anything else in there? No, I guess he's right. That doesn't make sense to me, does it?
Positive friction. Or maybe just change your coordinates.
Yeah. I think they should both be negative because that is pushing that point in that direction, and that is resisting the direction of motion. So that should be positive, yeah. Right. And then, yeah, my brain just shut off for a second, so this is a little scary about what's going to happen in the next hour and 36 minutes. So we don't know the tension and we don't know the acceleration. So we have an equation that's we're left with. I might go ahead and assume that I'm going to because I wasn't asked for tension, I'll solve for tension here so I can plug it back into something else. So we're going to have friction force, then becomes negative over here. That's going to get rid of that negative. So that we can write 22.07 plus our 9 times AB. Because we're going to want to know AB eventually. So there's going to be like equation 1 that we need. And this method is going to be, you're going to see this is so much more difficult than doing work and energy. We will have now, might as well put the other guy on the other box on here. And we're going to have now an FT2. Recognize that it's not the same cable. So we don't want to mistakenly think otherwise. This is going to be MAG. And let's establish a coordinate system, make this equal over into this side. We're going to have only acceleration taking place is going to go downwards. AA. And we don't have to care about the x direction, all we care about is the y direction. So we're going to have FT2 minus MAG equals negative MAA. These A's right there. Okay. So FT2 is going to be equal to, where did you go here? You're going to be 11.5 times 9.81 and then minus 11.5 times AA. So FT2, I don't have this written down, 11.5 times 9.81 times, looking back up above us. Yeah, okay. Yeah, I guess so 112.8 minus 11.5 AA. So that would be equation 2. So continued here. So we're going to go with, now we're going to have the main FBD of this guy, IBD. See, we might find out that what Jacob asked me would actually work in this set of circumstances, but there are others kind of similar to it where it wouldn't. But in this case, it actually was asking about Mike. Stop running this no, it wouldn't work. Okay. I remember why. Okay, so let's see. We're going to make this force, which should be that way or down there, is going to be FT2. And this force over here is going to be FT1. We could have the whole thing of MCG. And then up there, we would go RCY, and then I'm kind of pretty sure it's going to go that direction, so I'm going to put the arrow in there. It doesn't really matter. Here's RCX. And you know, there's in some instances it might be that we would want to know what these forces are on this pin, because we might want to design that pin. We won't care because we're trying to find the motion. So over here, we don't have any translation, and we're pretty sure that A is going to go downwards. So let's go ahead and make that assumption. Sort of I just call it I, and we're going to call it alpha. Because there's only one alpha, so we don't have to give the subscript. So all we have going on here is the summation of moments. Let's see if that's on. Summation of moments about C is going to be equal to I alpha. And this is I about C, so I didn't write it that way, but that is. So this is a totally valid thing, and we don't have to do the summation of moments equals the summation of effective moments, which is a thing that we might want to, that we could have used if we had all of the pieces together. But I don't think we should be using those pieces, mostly because something I will describe in a moment. All right. A moment. Not really a pun. Kind of. I don't know. I'll kill you guys. It's totally different. All right, cool. So we have that. We have that going for us. So remember that the convention is counterclockwise is positive. So we go FT2 times. Don't remember the name of the thing. Didn't give it a name. I guess we go RA. RA. You got to be a moment. We're going to say that this outer one is associated with this box A, so that's why that direction right there is RA. That's according to what I'm just writing there, and it's counterclockwise. This one is clockwise, so it's going to be FT1 times R. We'll call it B because that's what the box that's attached to this pulley is going to be. None of these other things, these all go through the center about which we're taking it. So we can come over to this side, and we can see that there's going to be a negative, no, it's positive, excuse me, counterclockwise is positive, a positive I alpha. So we could, this is equation 3. So, well, I didn't put numbers into there yet. I could go ahead and do it because I have equation 1 up. Where'd you go, equation 1? There, equation 1. I could substitute this guy in for there. And then I could also substitute equation 2. I do have a problem because I have, when I get there, I'll have 2 unknowns, which is, well, 3 unknowns.
Use kinematics to relate alpha and acceleration.
Absolutely right, yes. Cool. We can connect because we have this unknown alpha. We have, once we replace these unknown tensions, we'll have unknown acceleration of A, and we'll have unknown acceleration of B. Now, if we go back to the original problem and see how it's written right there, we want to find, knowing it's a determine the velocity of A. So actually, as a time-saving thing, we might aim for that right away and try to get everything in terms of A. We could skip like 1 step, maybe, if we do that. By which I mean, we'll take a little break from this. So it's like putting a pin in the thing and then going like here, go kinematics, because we just recognized we had to do it, and say that we know that the acceleration of A is going to be equal to alpha times what we just called RA, and the acceleration of B is equal to alpha times RB. But we'd like everything in terms of RA. So AA is already in terms there, but we could go that alpha is going to be equal to AA divided by RA. We could also say now that like, okay, well then, therefore, this is going to be equal to AA times RB divided by RA. Did you see that? I solved this one, and then I plugged him back into that guy. And now when I substitute this right here, I'll have A in the thing, and when I substitute this, I'll have A, and now I just solve for A. So when I come back up to this, and I go to my FT2, so that was my little, did a thing on the back. Now I'm back to the regularly scheduled program. I put in my FT1, which is going to be 22.07 plus 9 AA. Nope, AB. So instead of AB, I put in RA, which is AA, and then RB over RA. I could also, if I wanted to save myself itty bitty time, use millimeters for both of those instead of meters. But let's go ahead and stick with meters because that's how we started. So we want RB, which is smaller, that's the 150 over the 250 right there, right? 150 RB over the larger one. So I go 0.15 over 0.25. All right, and now I have that part right in there. All right, so I'm gonna have to go wide. Yes, now.
Are you doing FT1 or FT2?
You're right. My bad. I think I just made a brain blunder. So let me fix it. Okay, so I accidentally jumped to this one, FT1. I should have done FT2 right there. Boom. So this right here needs to change. My bad. Thank you for catching that. I would get all flustered and go into a shame spiral for not getting it wrong, but that's not true. Like I might, I don't know. Anyway, that was supposed to be, dang. Here, I see. Well, you know, you just try to do better next time. Okay, so that was my FT2, and now times RA, which is going to be 0.25 minus, and now we're going to do the one that we did before, which is the 22.07 plus 9, and now we'll substitute the AB. The other one was just straight out AA. Now we substitute the AB, which is going to be this right here, which is going to be AA times the 0.15 over 0.25. And then multiplied by RB, which is going to be the 0.15. And so we got that side of the thing. The other side is fairly easy. We're going to take that I that we found at the very beginning of 0.3812 and then multiply by alpha, but we want A, the acceleration of A. So we'll go acceleration of A divided by RA, 0.25. So all we have in here that's missing is acceleration of A. And if we do it, and we're very, very careful, hopeful, that's a lot of calculating right there that could go wrong. So I would sometimes do this myself in 2 steps for fear of losing focus. I know, hard to, and messing with it up. So I'm going to go 22.07 and 0.15 times, and see that we're going to subtract that from that. So I'll subtract it both. Okay, so I have that number times that minus that number times that. And so those are all the non-A things. So I got something like 24.89 for that side. Now all these other things, we have to combine stuff that are coefficients of A. That's how I think of it, at least. And that one's negative, and that one too is going to be is also going to be negative. So they'll come over here and they're going to add to this side right over here. So we're going to go 11.5 times 0.25. And then we're going to go, well, I'll go 0.3812 divided by 0.25, and those two add to each other. And then I'm going to go, this other last guy has got more stuff, and he's 9, I'll go to 0.15 first, then 0.15 times 255, and I'm going to add it to there. And I think I got everything, but boy, you can really mess it up. By the way, this kind of calculator works a lot better for that kind of thing. So, we got a 4.778. Boy, I hope I got it right. Crossing my fingers. Now, though, the original question, you'll recall, is it said, find the velocity, determine the velocity of the cylinder when it strikes the ground. So it's moved 900 millimeters, and I'm saying that it's got an acceleration of 4.778. There's a sanity check moment here. If it was more than 9.81, you knew you did something wrong, because that would be its acceleration if it was free fall. And it's got a couple things resisting it. It's got the mass of block B resisting, it's got the friction from block B resisting, and it's got the inertia of the thing rotating that's going to resist it. So it should be somewhat pretty less. I mean, that's anyway. So in order to find the velocity, we'd use the kinematics that look like this. That's an O. Plus 2 times the acceleration of A and times the delta Y of A. Like third day of semester. Yeah. So, a lot of said there. So anyway, we're basically going to take, we know that's 0. So 2 times 4.778, and this is 0.9. Wasn't that 900 millimeters? Sure. So anyway, I don't know why I just deleted that. Right? So 2, 1.778 times 0.9 times, good luck, square root 2.933. Oof. That's the answer. But this problem's better done, a lot easier, a lot quicker. It's a good exam question. If you this is too long and done in this method. There's too many things. But you can conceive of the basic ideas of the steps and connecting something that has the parts. I want to do. I don't want to use the time right now, Jacob. With your suggestion, I think it might be able to be done with Newton's second law by keeping the thing together. My big concern here is when we come to the moments. Let's see if I drew the thing. This is just for addressing that part right there. Right, we have to get rid of the ground in this. And you might see this and not be paying attention, and then do a problem and attempt it this way. Don't make sure you're listening and don't think. All right, some of the forces that we have going on there. Well, I guess those are going to cancel each other out. And this friction one is going to be that way right here, and we're going to have an mg right that way. And then of course right here. So actually, I think it can be done, Jacob. All right, because you're going to have no, we have the M A and the M B A. Okay, so the A over here. That's not going to matter, but we're still going to have the I alpha. Yeah, I think it can actually be done in one thing. So you can eliminate those tensions if you want to do it. But this is sort of a rare case for that. For doing the Newton second. Excuse me?
I think using a way could just eliminate the tensions.
Yes, you could eliminate. In this case, you could do it. Well, I was agreeing that you could do it. It's just in some cases right here, there could be. I'm trying to think of the scenarios, but it gets messed up when you try to eliminate them. But a lot of it. Okay, so one instance is if for whatever reason this thing was going over a pulley. You couldn't do it because the pulley has. Like, okay, so this is a one. suppose he has a reaction force, and you don't know the reaction force. And so you have to do it there. But otherwise, what you have in this situation is just right. 99.2647% confident. I'm holding out some hope. But anyway, if we were going to do the other way, K1 plus P1 plus U1 to 2 is going to be equal to KE2 plus PE2. That continued. You would set these up, you would go that KE1 is equal to 0 because it starts from rest. PE1 is going to be, well, let's see. The only thing that's changing potential energy is this. It's starting from a high potential energy. It'll go to a low potential energy. So you might as well call the bottom one the datum. And we'll say that it goes, so it's going to be 0 at potential energy 2. So here it's going to be MAG delta YA. So you're going to have 11.5, 9.81 metric, 9.1, so right, and then 0.9 millimeters onto the thing. And from what I have here, I have 101.5 newton meters is the potential energy. The next one, U1 to 2, that's going to be the friction force is the only external thing that's going to rob energy or add energy. Nothing's going to add energy, it's only going to rob energy from here. We already have the friction force. If we didn't already do it, we should go through this process, but I don't think necessarily I would take points off for not doing that. You just try to save yourself some time. It's kind of trivial. But I'm telling you, in general, in life, skip the free body diagram at your own risk. This guy just skipped it. Got it all wrong by half, you know, like, oh, well, it costs money or it costs lives, right? So, drop the damn thing. So you got negative friction force, and then you're going to go the delta travel of the thing, B. And so you got to figure out how much B is going to travel. So maybe we want to try to figure that out to the side. That is essentially kinematics, right? It's going to be the amount of travel that A does is going to cause an angular change in this disk. And, you know, so that's the amount of unwrapping that the rope of A is going to do. And and that's going to be the amount of wrapping equal to the angle times the radius, and that equals the amount of wrapping that B does. Did I say that to, like, you could say, so here's another aside, a kinematics aside, if you will. Let's say that this right here, this distance of B, LB, that's the length, well, I guess it is just going to be delta XB. Delta XB. Delta XB is going to be equal to delta theta times RB. All right, well, what is delta theta going to be? That's going to be delta YA is going to be the delta theta RA. So you can say that delta theta is going to be delta YA divided by RA. So we can plug that back up in here, put it into there. That delta XB is going to be equal to delta YA RA over RB. And actually, just as you look at that, you can kind of see where that makes sense. That these are like one goes up, one goes down kind of thing. They have a, but it's all tied about how many radians it has turned. So let's see, we have a value for this being 22, going to be a negative 22.07 and I didn't leave myself a lot of room. It's going to go 0.9, and this is going to be 0.25. I think I got this right. I might have. I'm starting to get nervous. I might have messed the thing up. Yeah, oh yeah, I did it right. Okay, and I think I get negative 11.92 Newton meters. Now, okay, so the kinetic energy at state 2. Maybe I want to give myself a little bit more room over here. I did quite a bit of unnecessary amount of indenting. I'll look at all the parts that are moving, and it doesn't matter whether it's going up or down or left or right, whatever, because everything gets squared. So we have 3 parts, and so we need to accommodate for each one of them. 1/2 MA VA2 squared. It's supposed to be A is traveling, plus 1/2 MB VB2 squared, plus 1/2, oops, I almost messed up, IC VC2, no, not VC, omega. Yeah. And we don't even need to call it anything because we only got 1 omega, omega 2 squared. You can already see that we have 1, 2, 3 unknown things, so we're going to have to connect these together with kinematics again. We might have wanted to write all of this separate in some other spot, so we didn't make such a mess. Planning ahead kind of thing. But I'm in the middle of an exam. I'm just going to I'll try to make it not too messy. And so we go to VA2, that's the thing that we want to find, right? That was the question. So we just leave him alone. So the other ones, we want to put them in terms of that. So you go VB2 is going to be equal to omega times RB. Omega 2 times RB, right? All right, well, that didn't help us any. But we do know that I should have done this anyway. VA2 is equal to omega 2 RA. That makes sense? These 2 statements I just made? So I can go, this one I can go, omega 2 is equal to VA2 over RA, and then I can plug him into here and say VB2 is going to be equal to VA2 RB over RA. Now we have both VB2 and omega 2 in terms of VA2. We would plug them into here so we can simplify and find that. So KE2 is equal to 1/2 11.5 VA2 squared. I'm sorry about that, making a mess there. Plus 1/2 9 times, and be careful with all the things that are going to get squared right here. We're going to get VA2 squared, but we're also going to get 0.15 over 0.25. That also gets squared. That's a common mistake I would make. We get down to this spot and go 0.3812, and then this last one, VA2 squared, and then this is 1 over 0.25 squared. get all those together, and I'm going to trust my former self. Oh, okay. I think it ends up to being 10.42 VA2 squared. And I'm almost home free. I have everything done except for the potential energy 2, but we know that's going to be 0 because we call that the datum. So we can go plug all those back in to the original equation for the kinetic energy, and we're going to get 101.5 plus a negative 11.92 equals to 10.42 VA2 squared plus 0, and we get VA2 equal to 2.933 meters per second. And that's not too terribly long of a problem compared to the Newton's second law problem. The Newton's second law problem ended up being too many steps. So I would try to figure out if I was writing a problem like that. I would cut it down. And it had some inherent meaning. So hopefully, I'm sorry if that takes too long. I'm going to use our
We do an impulse and momentum one as well.
I think that's a good idea. I got to try to. Oh well, we had to do a mass moment of inertia problem. But we'll do that one next or after that. I'll try to see something that's not going to be take a real long time. There's one where the solution doesn't really exist onto the page. It's on the practice problem, but isn't really. Can I change the thing? I wasn't sure I understood.
Are you doing a sign-in sheet, or is that kind of over?
Oh, we should. Yes, great, thank you.
Because Orlip, he counts it as a...
Yeah, sure. Well, hey, man, everything counts. Can somebody donate a piece of paper and start a sign-in sheet?
We get extra points.
Yeah. Let's put it into extra credit on top of the participation thing. It doesn't work out. It won't show up in Blackboard. I don't know how to make that thing do the thing I wanted to do. But I do all my stuff. I was gonna swear. Maybe I should swear some more. I don't know. That was last year's New Year's resolution. It is the 30th. Hey, you know tomorrow's May Day. I don't know. May Day. Yeah, I told somebody that my New Year's resolution was to start smoking.
Oh wow. Where's Little children made that for her.
Worse than Mary Jane Wanna. You're a terrible person. I'll be okay. Everybody I drive behind seems to be smoking nowadays. That's amazing to me. How it's so much smoke. And I don't even think the windows are down. And I could totally tell. I feel like if you ever watch On Patrol Live, I feel like I'm who's gonna Danny Brown on Patrol Live. He can smell.
I was just praying no one feels that pen. I like that one.
Oh, she likes that. I saw a new pen I want. Dr. Asaki uses these really nice. I covet his pen. I took a picture of it.
What's it called? Yeah, I covet?
No.
Oh, you covet it.
Yeah. It's like a lash.
Oh, I was gonna pass it around. No, I've already started. Oh. I know I was supposed to take.
Well, I also saw something I really want. Anybody at the?
I was at a party. I mean, it was. Everyone just gotta get drunk. I think.
Wait, Helix?
Below the pencil.
Well, that's a pencil.
Have that pen? Yeah. That's a nice pen.
I thought that was a gun.
Oh, you don't think it's a nice pen? I'm easily impressed.
Hey, it's a very nice pen.
I saw today biomed
Causes and dynamics. Okay.
professor was doing his teaching demonstration. He had a way to hook up his phone to the overhead projector.
I feel like either way I'm still gonna fail the class. I know you're
TikTok things.
Wish I fell in my head.
And Dr. Asaki says I could do that. I'm like,
Yeah.
what the hell?
I think he's gonna go.
Man.
I think he's no. I
You should have
don't.
taught me how to do that. That's why we're here.
No, I think.
All right, so we're gonna do this upside down.
Listen, I'm not fine, and I need to pass.
And find the mass moment of inertia. It's a pretty straightforward problem. You would think it's a straightforward problem. Depends what they're asking for, right? Okay,
Think about it. If you get
this looks like something I did back in the day. It has a number of features that are indicative of me. Back in the day, that I used to write, like ask for every step.
Sasaki.
All the in between. I don't do that anymore. But here I would go. So we got that T. That's
A
like
6K on the second one. That counts as like probably 60%.
You know what this makes me think of? Of course, it's not
60% out of the 40%
anymore. Judas.
At least the D, and then with the curve, a B.
That's not true. No, it was Paul.
Girl, that math made no sense to me. I'm not gonna lie.
I remember my boss.
I don't know how it's gonna be.
Not like upside down crosses, like. So we want to find the mass of the assembly, and okay, so what is the thickness of this? T is 0.1
For children,
meters.
I don't know. That makes sense. Why would you?
Density is 1,000 kilograms per meter cubed, which I think
You're only
is
gonna wear it
actually
once to accessible for a week.
this pivot's about the hole that's in the top. We're going to ignore the fact that the hole, how far that hole is from the top. So I'm just going to make it look like this, which you can't see yet.
It goes higher in value. Is it limited?
0.15 meters wide at both spots right here. 0.15 and. So I feel as though I was mean in the past. I don't know. I'm kind of angry at him. I must have measured. I must have taken a measurement. It doesn't tell you what year this was either. All right. So we want to find A, the mass, B, the location of the center of mass, and so that's all that we really need is the Y, because we know the X, obviously, where the center of mass is going to be. C, the mass moment of inertia at the center of mass. B, D, oh, that's hard. We're going to go I, and this, I'm going to call that A, so I'm going to call that A at the top, and then the radius of gyration.
Are you
So there's
supposed to
a
be
lot.
showing us your paper?
Excuse me?
Is the paper supposed to be on the screen?
Yeah, not yet.
Okay.
I was just narrating as I was writing it down. Because I can't, actually I could just read it right here, you know, that's like, I just hold that paper up. Been a long semester. Am I going to make excuses? Sure, of course. I'm going to blame Dr. Asaki? Yes. Because I would have been so much more prepared, wouldn't I? Right? No? Yes? No? Wait a minute, I don't know where this was supposed to be. It's about the pivot hole. Okay, so this is the radius gyration about the pivot hole, which I have decided is going to be A. All right, so the best way to organize if you have lots of parts is to make a table. I don't know if there's enough parts here to justify the table. I will make this decision right there, which seems obvious, but, and I didn't label how tall that was. So that's 1 meter. Right there to there is 1 meter. But there are some crazy people that might split the thing down that way. The point I'm making here is that sometimes with some parts there are a variety of ways, and maybe a simpler way than other ways to break the thing up into parts. This is the simplest way to just place it right there. And so to keep track of the thing, I'll call that 1 and that 2. Not 100% necessary in this, but sure. So I guess maybe I'll go ahead and figure out what mass of 1 is really going to be 0.15 times 1 times the thickness 0.1. Right, so that's width times height times depth times density. Right, because if that's volume times density, we can all agree that must be the width. That's something funny I was going to say. It's something I is immediately distracted by myself. 0.1 times 0.15. I think the only person that's more amused by me is my wife. That's good news.
How's your wife doing?
She's doing pretty well. Trying to think of something new that's going on.
So you
She's
want
a happy person. She's like happy all the time. She's Mrs. Positive.
happy wife, happy life, huh?
Happy wife, happy life. She's a happy person. And everybody likes her, by the way, too. It's a little weird. You know? A lot of people don't like me.
Really?
Sometimes I could be a jerk. Hard to believe. Try not to. Try to be a better person. I apologize a lot. All right, so this apparently has all the same dimensions as this, so you can save yourself a little bit of time. This is 15 kilograms. But here I am writing it out anyway. Not saving that time. And therefore, m tot equals, oh, dude, in my head. And here I am putting in the extra unnecessary, but meaningful to me. Ooh, I got the right answer. See, by the way, this is like this is an old school SolidWorks. I don't know how long ago SolidWorks that was. This is probably before I knew how to screen capture. There was a time when I didn't know how to screen capture. Back in my day, we didn't know that. Never shut up. All right, we want to find the center of mass. So we get the total. We find that. There you go. Cha-ching is part A. We want to find the center of mass. We could do that with this great little equation: summation MIYI summation of MI. Of course, this is actually summation MI. It's actually that one right there. We just skipped over that whole idea right there. But M1 plus M2, MI. Right here. So you can go like, so you go 15. So this is 1. And where is 1? Well, we want to take, okay, so it's always a good idea to establish the distance, the location of where you're taking the distance from. And if you go back and read the original problem, it says distance from the hole. That's really the spot that it would matter. Right? So you don't want to do it from the base. You want your reference to be from here. So we'll make that yi, where the distance to the center. So that's going to be 0.5, right? That's the center of 1. And then, just for the simplification here, this is the same mass of the thing. And so, but this is going to be M2 times Y2, and Y2, and this is just an itty bitty different change here. It's not going to be equal to 1. It's going to be 1 plus 0.15 divided by 2. I don't know if I was a jerk and taking points off for that. Maybe a little half point. These little things matter. These little details matter. I don't know. Does it matter? Does that change someone's academic life forever? It's 0.1. I don't think so. Anyway, get 1 plus, because it could be a real small amount. So it's 1.075, all divided by 30. So when you go 7.5 plus 30, I think I'm going to screw this up. I think I get it right. Take a look at this. No! How did I get that wrong?
You have to subtract the whole.
I didn't actually include the whole.
Okay, so that's just like a reference point?
That's just a terrible drawing. That's like someone is just making problems for the first time in a dynamics class after years of being sitting behind a desk kind of engineering.
Should it be 0.075?
I don't know. No, it should be +1 because we're taking it from here coming down.
Point zero
So
seven
I gotta see what I did wrong here. I took a shortcut, I think. I went 15 times 0.5. Well, 15 times 1.075. That sounds right. Add them together, divide by 30. Yeah, okay, good. 0.7875 meters. And that according to, whoop,
Is the second y or y2 from point A or from zone
from A. Because we're doing it about A. And I don't know why I didn't write that number down. But I wrote it down, then deleted it. No, I erased it. And then I put it back in there. But anyway, if we take a look at this, I should have put more decimal places into the thing, but we got the right answer. All right, so here comes the hard part. Well, not necessarily the hard part. I think that the easier part to do here, right? And if I didn't write it out, so that's good. I think I would have done it the harder way back then. This is the easier way to do. Is to do it about A, and then have it all. So answer part D first. The mass moment of inertia about the pivot hole. Do that one first, and then move it to the center of mass. It's an easier way. So we're going to go IA. I'll write it out as symbols. I was doing it as numbers up ahead. It's going to be I1 plus M1 times, I guess I'll just call it D1. You know, what I call this varies a lot of times, but in many books, D doesn't mean a diameter, it just means the distance that you're going to move that thing. And a lot of times, if you set it up in a table, it's going to be the same thing as this Y, as something else. And a lot of times, it's going to be this Y. It's contextual. It depends which you're using, but in this case, it would be the same thing as that. Plus I2 plus M2 D2 squared. Now, here you got to make a decision how much effort you want to put into a problem and if it's going to matter. They, being me, gave you the width of the thing, but these are pretty slender. 0.15 versus the width of the thing of 1. That's right there in the kind of like, do you treat it just like a slender rod or do you treat it like a rectangle? Because it's going to get, because the width of the thing is going to be, you're going to square that. That's a small number. And so it would make a difference, but the complexity, okay, let's go ahead and do it for accuracy, but recognize that I might make some statement. Me today would make a statement going like, you know, approximately, right? And so I say approximately, and I'm like, ooh, hopefully you know that I'm giving you license to make some approximations. I don't know if I would do that. Probably. All right, so we're going to go 1/12 times the mass of 1, which is 15. The mass of 1 is 15. I don't know why you're holding it. Times the length squared plus the width squared. So 1 squared plus 0.15 squared. So you recognize that right there. If we just treated it like a slender rod, we would just go 1/12 15 times 1 squared. But we're going to say that it's a rectangle, like that the width of the thing will matter. But it's 0.15 squared. It's not that, not a lot. Okay, now we have to move the thing, so it's going to be the 15, but we're going to have to move it 1/2 of its length, or 0.15 squared. Right? Because we're moving it, the center of mass with that guy right there. This is the maximum of inertia. We're taking it about that spot, but we're moving from here to right there, so 0.5. So that's what we've just done right here. I'm going to go down to the.
In that case, right?
Excuse me?
I said that's d the 0.5 squared. Like the variable d you have written.
Yes, that's the 0.5. That's the D1. Yes, I think that's what you're saying. All right, so I'm going to do this next thing down here. This is actually going to be the same value, just coincidentally, because they look the same. Okay, so 112, 15, 1 squared plus 0.15 squared. Right. And now plus 15, and now the distance that we move is going to be the same thing as we move right here, because we're going up to A. So 1.075 squared. So I can find it about the whole, and I can take advantage of the fact that these are the same right here, so I can just hit times 2. EV, and so I go 0.15 squared plus 1, and then 15 times 12 divided by 2 times, right? So I have that and that added into it. So now I'm going to go 0.5 squared, which should be 0.25, times 15 times, and then add that in there, so remove it. And then 0.1075 squared, 15 times, boom, and that's like the majority of this thing, and I got 23.64 kilogram meters squared. How do we do compared to SolidWorks? Okay, cool. Look, we got in here 23.64, so we got the right answer.
Will you guys be handing out the sheet with all the mass moment of inertia equations?
I do, yeah. I'm not 100% sure that Mark Romup uses it, but I'm pretty sure he does.
I think he does, because I know he tells us how we can make our own sheet, but then he also passed out one that if he didn't. So I don't know if he passes out that one as well. So
Yeah, I'm not sure.
I guess
I always need to ask him details like that.
Are we allowed our own sheet?
Yes. You like him better than me? Okay. Sorry. How dare you? Our last, well, not quite last thing. Well, we could actually jump ahead to, because we jumped to D, we haven't done C yet. So, but while we're here, let's go to part E, where we're going to try to get the radius of gyration. And remember that the radius of gyration is sort of like, I should have fitted M in there, right? It is a shorthand way of writing out the mass moment of inertia of something, where you say, well, if you had like this thin disk, what would the radius of it to be, with the same mass, what would the radius need to be to have the same mass moment of inertia? So that's what that is. But it's also, what we're able to do is find it by taking the square root of IA over M. So square root of 23.64 divided by 30, and what would we have? 30 square root. Only a 0.8877 meters would be the radius of a thin hoop. That would be the equivalent. And then finally, the part C, about we want the mass moment of inertia about the centroid, or the center of mass would be more appropriate thing to say. It is in fact the centroid of this. And for that, we need to use the parallel axis theorem to go from. So that would be IA is equal to this right here plus the mass times the distance squared that you need to move it, which is actually going to be y bar that we have to move it, right? We got our y bar from A, So now we're going to move it. We found the mass moment of inertia about that spot. We're going to move it to the center of the thing. So we flip it around here and we go, that is equal to IA minus M times Y bar squared. So, and remember that one of the reasons why we're doing one way that we can remember that we are doing, that we are finding the mass moment of inertia about the center is that is going to be the smallest mass moment of inertia. That's the easiest place to spin the thing. So it's going to be a smaller number than doing it about A. So we take the 23.64 and then minus our 30 and then times our 0.7875 squared. And 23.64, 0.7875 squared 30 times minus fingers crossed. That's what you lie, though. You lie and you hope with the same gesture? Doesn't make any sense. I never thought of it that way. Kilogram meter squared. Let's see if we got the right one. Oh, got it. Wow, what a sense of satisfaction. I wonder how far off we would have been if we treated them like thin rods. Let's just imagine that we did. Let's go find the result. I think it will afterwards. What would we like to do? Oh, we want to do a collision. We said we want to do a collision, right?
Yeah, impulse momentum.
Yeah. I don't know. Want to invent a problem? Want to look at? We could go look at must. Look at the guy that does Captain Underpants. I don't like the way, by the way, in the solution how Dr. Garcia writes out some of these things, but I never bothered to rewrite them out. She wrote these. This is her handwriting. Over here.
So, when you go back into the problem, right? Like which one is I, which one is I bar?
Yeah, that's a good question. C is above the I bar, center mass, and the other one, what I called IA, I didn't label it. I said I'll call it A. Why not? Could call it O. O might look better. That would have been D. Extras and rejects. Yeah. What is must problems? I forgot I had this in. I don't have the answer on top of me. This one, let's see, what is it asking? The system originally at rest, the 100-foot couple is applied to drum C, determine the speed of the center after it is rolled 5 feet. That's going to be work energy, don't you think? Because they're talking about how distance that it's moved and its speed. So we don't want the acceleration. We don't want the hassle of, so you couldn't use Newton's second law with just the assembly because there's 2 points of support right here and right here. And you want to eliminate the points of support, but you can only do it one time with the summation of moments. All right, so that's kind of like the reason why. So in this situation, we couldn't do it. In the other situation, I think we can. This is an impulsive momentum. It's a little straightforward, and I don't think it's a rigid body one. So I don't know how it made it into here. But it is an impulsive momentum right here. You can find this is like a 3-minute problem right here that you could do, right? So this is the kind of problem you find in the fundamentals of engineering exam kind of thing where you try to most of the time for that you have an average time of about 3 minutes to solve a problem. So you mostly just a single or 2-step problem onto this. We could do that if you want, but let's the time. This is a spring. Almost every time I see a spring, I know it's a work energy problem. Pretty sure. Wrapped initially. So as determine the maximum stretch. Oh, maximum stretch of the spring. That's interesting. I guess that, yeah, okay, yeah, because that means where it's going to stop, right? So kinetic energy at the state 2 is going to be 0 in that problem. This is a rigid body acceleration. Rigid body acceleration. Ooh, that's all I had? There, we have to go to must. Find some more. Unless somebody has one, or, well, I don't know. You memorized some problems, didn't you? That's what you did.
Maybe like a homework problem?
Yeah, sometimes the homework problems are too long for
Yeah,
problems. Let's see. I did, do we want an impact problem is what you said? Is that what you asked for, or just an impulse momentum problem? I can't remember now. I can't remember.
Impulse momentum.
I can't remember what course we're in.
I think there was some a part of the practice problems you posted.
Oh, in some of these?
Yeah, if you go up.
Okay. Yeah, here's one I kind of liked. This is how my man Sean did this one. See, I was going to do this one right here, but I think I did one already. This is one of mine. Here's the impulse momentum problem. This is Dr. Garcia. Let's do this one. What do I say? All right.
Oh yeah, perfect.
And also the solution that I have is hers that's posted. And it's not like she's wrong. She just had a certain way of doing stuff that I think I don't know. I don't think it was as easily understood sometimes. Her solution right out. I think it looks like her. Yeah, it looks like her handwriting. I saw her last summer at the in Baltimore at a conference. Her son used to just worship the ground at one time. His name was Skyven, and he'd come into my office all the time and ask me all kinds of questions. I had a bunch of toys in my office. They weren't necessarily for kids to come by. That sounds kind of creepy. I also kept, like, I didn't even remember I kept this like little razor blade thing. A little razor blade knife. One day he's just playing with my toys on my bookshelf, and he picks up in here, and I hear the click 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 of the little thing come out, and I turn around, he's got this blade. I'm like, ah!
How old is he?
4.
Oh God.
Years old. Alicia was not happy. But I confess, I could have tried to hide it. So you're not going to believe what just happened, and I'm so sorry. Omega 1 here is going to be 4 radians per second. I guess I could actually, as I just told Shelby a minute ago, I could write this out while, so you have something to do while you watch me talk. Could, unless I don't have it here. Nope, it's right there. Nope. Nope. Where'd you go? Skyver doesn't even remember who I am. So bad. All right, so elastic, let's see, mass of what? Mass of this thing is 7 kilograms. The mass of the ball, MC, is going to be 2 kilograms. And it's at rest, and the coefficient of restitution here is 0.8. And determine, so our find is going to be the angular omega AB, let's call it 2. And okay, and the velocity. So this is really the one we care about. Who cares about what the angular velocity of this rod is after the thing? We only care about the ball, but we call it C2. So one thing to do to get out of the way, I think, And recognize that it's going to be make our lives a little easier, I think, to find the mass moment of inertia about A of this piece. So let's just go ahead and do that. Let's pretend that we know that. We know to do that.
So that we could say IA is going to be equal to, and we're treated like it's slender because we don't know the width of the thing. So you go 112.
And instead of writing out the equation, I'll write out what the values are. I'm not sure if every professor wants us doing that, but we'll do that. So we have 3 squared. And in fact, by the way, you could do a little cheat. You don't have to do it. Do you know what the actual equation about the end is going to be, as opposed to about the center?
Moment?
No, I'm just saying, like, okay, you know for the long one we go 112,
Yes.
and then mass times length squared.
Yeah.
What else would you believe instead? How about 1/3
BH cubed.
mass? Like, you have BH cubed over 12, BH cubed over 3 is like, for a rectangle,
Yes.
is BH cubed over 12, but if you do it about this, it's BH cubed over 3.
Yes.
About the end? It's going to be the same thing here.
Oh, because it's fixed at the end.
Yeah, because it's right at the end. Okay. Cheater. Could be a cheater. Not cheating. It's just math, right? But anyway. So we're going to go 3 over 2 squared as part of that. And that's not what Alicia has. She did it about the center. Oh, no, she did it at some point. She says it's going to be 21. Should we trust her? No, can't trust her. I have trust issues. So 9 times 7 divided by 12, boom. And then 1.5 squared times 7 plus, wouldn't you know it, Alicia. She's right. Okay, so I think the 3 diagram method for this.
Did you explain that extra 7 times 0 over 2?
Okay, so I'm going to take this mass moment of inertia about A. So I'm doing the parallel axis theorem right here. So this is about the center.
Oh, that's not I bar, it's I.
This is I, okay, IA. So I took I bar and I added the mass times the distance I had to move it over from the center, which is 1/2 of the length over there. You're right, I'm getting loopy because I'm tired. But, sorry. I volunteered to do this. Stop complaining. Stop talking to yourself. So, does anybody have plans to? No, you guys aren't grad. I was about to ask about what you're going to do for graduation. And I forgot. You're not graduating. Not yet. Not yet. Close, so close though. You're halfway. You're almost half. When you do graduate, so you can plan ahead. Are you going to wear something funny on your, are you going to do something, write something funny on your hat? Make it light up or send some message. You might also be the kind of person, if that's the case, that has bumper stickers. Read what my car says behind me. Has it ever influenced anybody? See, I don't know why I put the AB in there. See, there's get rid of the AB. Just put omega 2. There's only one omega thing going on there. You don't need that. Omega 2. Omega 1. No. Omega 1. And we know that to be, okay, so we have that. And that looks like the W. I have a lot of people still, hope, none of you, some people I know, keep calling that W. We're going to try to stop that. Make it more look like an omega. Okay. All right, so these two are going to hit each other, kaboom. But they're equal and opposite. We're going to say that this doesn't have any kind of effect on it. We should label these, but I'm not going to. And then when we're done here, okay, well, I would say the sensible thing to do is to all of a sudden for this time decide that clockwise is going to be positive. Can we all say this one instant for convenience, stop writing negative numbers? That clockwise is positive. And actually it kind of belongs like right there, by the way. X, Y, so there you go. Clockwise is positive. So we're going to assume a positive direction as the result. Let's just assume this thing keeps going around and moving in the same direction that it was after it hits the ball. But we can realize there's a chance it rebounds and goes the opposite direction. Depends how big that ball is. All the numbers in the variety. And let's also choose that this is the one that makes the most amount of sense, that we're going to have that thing right there. So, okay, I think we're ready to write the equations for this. So this is AMOL. And so it does the summation of, do I want to write this whole thing out? Yeah, I did. All right. So this is going to be HA plus integral of M dt equals summation 1 HA2. Guess I can parentheses there. This doesn't matter. Okay. So, looking at this carefully, we can see that we got and we've decided that clockwise is positive. So IA omega 1. Nothing happens here, right there. Okay, cool. It's going to be equal to IA omega 2, and then this is positive MC VC2, but we have to also have times the length. Right, because we're doing it, this is a linear velocity, but we're looking for angular velocity, so we need a distance to multiply it by. So we'll take our 21.00 and take our 4 radians per second. This looks like a foosball table, not a foosball, no, like a pinball. Like a pinball, except really big, like huge, like stupid big. We get omega 2 plus, this is 2, and we don't know this, and this is 3. And so we can come up with an equation that's, I believe this is going to be 84. And 21.00 omega 2 plus 6 VC2, and we're kind of stuck. We need to connect these two things together, but the real thing that we're going to add into it is the coefficient of restitution. So we put in the core, which we have to be careful when we're doing impulse and momentum or collision things. We have to use the velocity of the part of the rigid body where it's hitting, not the, it has to be the localized one, right? It's the collision velocity location. So I think I'm going to call that B, because that we call the end B right here. So that's going to be the localized velocity BB2 I'm talking about is that spot right there. So let's say that we have BB2 minus VC2. I think I just messed things up, but that's okay. VC1, which is going to be 0, minus VB1. And recognize that VB is going to be omega times L. Because it's the kinematics of it. It's just are fixed into there. So this thing is, the ball is starting at 0. I could have flipped them over. Maybe I so this is what, 0.8 equals, okay, here's a VB2, we don't know that, minus VC2, we don't know that, divided by 0 minus, and that's going to be 4 times 3. Right, that right there is the angular velocity times the length of the thing, the initial one. So we will have the equation, I guess VB2 minus VC2 is going to be 12 times 0.8. Should do it in my head, not gonna. 9.6, but it's going to be a negative 9.6 just because of the way I chose to flip. I'm going to flip those around and make my life easier. So that's going to be 2. But we also, so we have VC2 and omega, VC2 and VB2, but we can replace that VB2, VB2 is equal to omega 2 times L. So maybe I should have made this other one too. And so we could go omega 2 times 3 minus VC2 equals negative 9.6. So I'm changing my mind. That's V2. So we were 1 and 2 placed together. Let's see, how would I want to do this most easily? Well, I guess it doesn't quite matter. It looks to me like I could.
We solve for VC2, so we can solve for omega 2.
I think so. That's easy. You're right. VC2, bring it over there, and you go omega 2, 3, and that should be plus, right? And then stick that back up into the top right here. So 84 equals to, all right, so 21 omega 2 plus 2 times, sorry, 6. Oh. 6. Now right there. Times omega 2, 3 plus 9.6 and omega 2. Concentration. So we have 84 and 9.6 times 6. Multiply that by that right there. And that's going to come over here and be negative. So we'll subtract it out. What we're left with is here's omega 2s. So we have 3 times 6, so 18 plus 21. And divide. So my omega 2, if I did it right, was 0.6769 radians per second. And it's positive. So if I did it correctly, maybe I did, I got the answer right here. Yep, 0.677 is what Alicia has for that. And then I could go back and plug it back into this one. So I'm going to multiply that by 3 and add it to 9.6. Boom. And so my VC2 is going to be 11.63. Meters per second. And it agrees with Dr. Garcia. We got 0.667. I kind of wish I had assign homework 24.
If I split it into, my class,
Disparity between classes. It's all coming to the head right here. We're all going to get it pitchforks and torches if you want. Storm the castle. Unfair, unfair. Sorry. But there'll be a little difference. We tried our best to coordinate that thing. But yeah, this is a good standard problem. So you should be able to solve a problem similar to this.
What's a good indicator that you're gonna need like kinematics and rotational impulse and momentum?
I think you almost kind of always use a little bit of kinematics.
Yeah, you start off with it and
Yeah, but this is the simple one, which is nice, where it's not a complicated one, but there can be problems that have...
on the homework, you needed kinematics, linear impulse, and then rotational one.
That's definitely what happens when you have a problem like... I'm trying to remember the ones that we had right here. Because you've already turned in all your homework, right?
Yeah.
I don't... See, Dr.
so I can argue this one, make that film, right? Yeah, sure. In this case, let's see, for this guy,
Yeah, this is the one where you needed, so this is a more complicated problem than the one I just did, because it's got translational and potentially
Yes.
so you have these translational momentum, angular momentum, and impulse.
But it's not easy, but it is a fundamental problem. Like every single dynamics person taking dynamics should be introduced to this problem in rigid body
Impulse momentum, it's just,
I'm going to use the word ubiquitous, because yeah, the pin problem is a lot simpler, right?
Yes.
But you know, we want to, at the same time, you know, I don't want to go wax philosophical, but that's kind of what I do. Like, you know, the reason why we're here
to be in this whole process is not necessarily to be trained how to do this problem.
Oh, you got to know this problem. Oh, you cannot be an engineer if you don't know how to do that problem. It's really not the case. There's really, you know, it's more along the lines of like you want to raise the level of, you know, you can be a person that would solve a problem like that. And that will help you when you go to solve other problems that have nothing to do with this. Yeah, got it. Anyway. But I'm saying that out loud for my own benefit, to remind myself sometimes that where I have this, oh, we've got to teach that. Well, we were doing a disservice if they never learned to do that. Like, yeah. It's a type of thought process. All right, let's look at other problems to do. We can, or I could talk about some other homework problems and explain some things that you have.
Could you just point out which practice problems would be like constant acceleration?
Okay. Oh, okay. Yeah, sure. You mean rigid body acceleration? All right. So there's an acceleration problem, and this is one where it'll challenge you a little bit because it's giving you the piston. Although I think maybe on my exam, I think I actually asked one that was like that. And this does have the simplifying ability. One aspect this makes it overly simple. I think generally this rod has no angular velocity. How can I tell?
because it's not moving itself.
It's more along the lines of let's say the ICR. Can you find the ICR?
Now, the infinite ICR.
If you draw a line perpendicular to the velocity at B, you draw a line that's the velocity to the velocity at A. Those lines perpendicular are both going to be parallel. So it's never going to have an ICR, and therefore, at that instant, it doesn't rotate. And you're like, how is it not rotating? It's because it's transitioning from rotating in one direction to rotating in the other direction. So it's just at that inflection point where it's going to have no angular velocity because it has just changed in the direction of its angular velocity, the way that it landed. So it really simplifies the problem. You don't have a normal acceleration to deal with in the rod. You do have a normal acceleration here, but not in the other one. Yes, ma'am? Me too.
Oh, I got it. Will there be like an ICR, like a question that asks specifically to use an ICR on a test?
No, but probably you will have. It would be the simplest way to approach the velocity analysis for the problem. I think that's fair to
For an
say.
acceleration problem?
Yeah, acceleration problem. You need to get the velocity. It's a complete problem, right? So like I didn't ask that on exam 3 because I want to specifically ask an ICR problem and I want to ask an acceleration problem. So in the acceleration problem, I give you the angular velocity so you don't have to do it twice. Here I'm just going to ask you once on the problem. And it is kind of related a little bit to the type of the mentality. I'll be free to admit that, like, you know, oh, well, I want you to know how to do this because, well, every good engineer should know how to do that, but there's a certain amount of, yeah, I got it. I know what I just said a second ago. But I do, it's one of my priorities. Yeah, I think that was the only practice one that I saw, and there were the other exam prep problems. I had a feeling that I had practice a final exam practice problem. So I had that one. I guess that was the only one in there. Yeah, I would just suggest going back to some of the stuff from exam 3 to move in there. I misremembered I do think that this must is a great resource to be using for practicing for the exam. And honestly, you know, when you go to other courses, that's a good idea to like try to find somebody else's. You know, Purdue does this crazy amount. Although they approach a lot of courses very differently, but if you go to Purdue, all the students at Purdue have put together all these exams, like this tremendous amount of exam, I don't know what to call it, collection. I'm trying to think of the other name for it. Archiving, like and the solutions. And I think that all the students all the professors are okay with it because when on their like course webpage, at least for dynamics, they link to it. Like, you want to see the solutions so you see all the exams? And they call them weekly joys, and I don't know what that means. If you look up on Purdue's website right here, so weekly joys are Purdue weekly joys. It's a weird name. Weekly joys practice exams. There you go. This archive.
Oh.
I don't know what the hell's what have you been looking on the internet?
Exactly.
But if you find the dynamic status, look at this. These are all courses right here. I think I do have a link to this on my Blackboard, by the way. Yeah. I'm trying to understand. I'm sorry, my head's not quite into it right now. Yeah. Well, they make a lot like the stuff that was on exam 3. So like the practice problems that, you know, generally try to find something that's within the range of doable, and you know, I probably will leave it up to you which method that you would use, but I would prefer to see the 3 diagram method for the acceleration parts, like ICR for the velocity, so you can get the omega that you probably need, and the 3 diagram method. And I usually try to find a way to make it so it's not a super long problem. So there's usually something aligned with one of the axes at least, or two of the axes so that you don't have to have a simultaneous solution to two equations with two unknowns, but instead one of them is just inherently going to be zero, so that like you're able to solve that one and then plug it back into the other instead, so to speed things up. So I don't know if that helps to answer.
Yeah, so the acceleration problem like won't relate to like doing second law?
No. I'm going to do that. I'm going to do it separately. And it's not that like, it's most of the time it's because students weren't able to do it on exam 3, and a certain percentage weren't able to do it. And I want to emphasize, hey, so like for instance, you could just leave it blank, probably on exam 3, and it might have been worth 30 points. So you just went, I'm just going to take a 70. Okay, that's your choice, I guess. And then you see it on the final exam again, and you're like, oh, 25. I'm just going to go ahead and take 35. Just completely avoid it. I'm going to try to make it unavoidable, right? That you have to be able to do. I know it's difficult to do, but I want to measure your ability to mastery of the whole subject, and that rigid body acceleration to me represents a whole lot of visualization, taking a difficult thing, picking it apart methodically and coming to a solution is something that's not an easy thing to do, but also if you can do it, it shows, yeah, you got this. Yeah, you're good. You can take all kinds of problems, the next things that get thrown in your way, pick them apart systematically, think your way through, organize your head, and be able to do that. So that's my thought process.
My second one was like, what's the difference between regular impulse and momentum and an impact problem?
All right, great question, because a lot of times the impulse momentum will just be about like maybe an external moment or something that has caused it to, move, or we could, usually something along those lines. It could be just like gravity or something, or like a cable wrapped around something that's making the thing spin. But the impulse, the impact one is usually going to be some collision involved with an object. And almost always it's going to be a particle that's colliding with the doohickey, or with the rigid body. Because I wouldn't want to have two rigid bodies colliding together. It makes a long problem. It's a tough problem. The fundamental thing to watch out for in the rigid body collision problem is to make sure that you're using the localized velocity of the rigid body as part of the coefficient of restitution. That's the spot. The coefficient of restitution doesn't care about the angular thing. It just cares about what it's seeing right there where the particle is hitting it. So that's the velocity that you have to put into the coefficient of restitution to be able to get it into interaction with the rest of the body.
And it's like the impact problems that have the linear momentum and the angular momentum? Or is that only for like the momentum?
Only, so I have other people besides my class, so I can't rule out for everyone the same thing, but I generally wouldn't ask that problem. I can't think of a scenario because it's too long of a problem to ask. So given an infinite amount of time, and I don't know, it doesn't matter. I usually would ask a pinned problem instead, and make life a little easier by moving the moment of inertia to the pin, or making it about the pin, so I can just take a couple more seconds off of the amount of time that it takes to do the problem. Okay. Anyway, I was going to find the weekly joys. I'm going to get away from those feet, though. I'm not judging, just saying. Feet aren't bugging. But yeah, you can see some of the. I don't know if he has many collision ones in here in the must. One that rings true for the collision, like the most classic collision problem in rigid body is the ballistic pendulum. because it's like an old problem. It's a problem that goes back, like before even guns, back to cannons. I wonder if they probably did the same thing, because they were trying to figure out, design the perfect cannon, or optimize it, you know, and like how do we get it? Well, that's how, you know, I'm sure they could shoot it how far they want to see, but let's we can hit a pendulum and see how high it goes up. I don't know that for a fact. I'm sure that there was at some point people who were working on that type of thing. You actually don't see many collision things
Have a
in this.
good night. Thank you.
You too. Thank you so much. Yeah, I don't actually see many collision things here. It doesn't really do one that I see. Yeah, it's not as common. There's not a must problem for it, but you could probably find one in the Purdue people. They're really that's. Oh yeah, the Washington University, these people are nuts. This one is great. If you want to have like a little laugh, I'm not long laugh over here. But you see some of these final exams, and some of this is like I don't know one guy from another. There are a couple of people here, but some of it has like, yeah, we're not doing that and right here, but it's like sensing a disturbance in the force. May the fourth be with you. A Jedi abandons his battle and makes the fire and rushes to the rescue of the oppressed petting zoo animals on campus. And some of these must be inside jokes too. How bad the food is and the comments and that type of thing. But they're all a continuing story as he goes through and all that. I don't know how effective they are measuring students' ability. Seems like a little bit of a distraction. But you see the ask for 4. There are some things that we don't, there are actually 3-dimensional questions on here that we don't cover, but I don't feel like you're missing out, I don't think you should be too saddened by that. You just look how happy she is though. You know why? She owns a hovercraft. And I want that hovercraft so bad. Did you ever see The Office where he like falls in love with the lady that's in the chair catalog? And he gets Dwight to try to find the lady in the chair catalog. That's where these people are. So I'm not in love with. I'm in love with my wife. But I want to see this woman. I wonder if she's that happy all the time, or just a really good actress. But she doesn't have a hovercraft. I used to have one. So I even show, as this exposed, I usually hide this. Did I actually show these? Some of my favorite things in the world. This is not Mr. Positivity. Do you ever read these? Anybody? Nobody? No? All right. I have this up in my office. It could be that the purpose of your life is only to serve as a warning to others. Here's your Purdue. Here's the dynamics. Here's their course page, and they have links and stuff, concept questions. You can see what another school is doing. But I'm looking. Here's exams, and you go. Here's what they say. Here's their equation. Here's the sample exams. See the weekly joys. Okay, so here's the dynamics. So you don't have to look it up. Boy, there's more feet right there, but at least they're not so puffy. ME274. Well, look at all these. Look at all these exams. Look at all of them. Gosh, we should do that, right? You should get some students to put together all this stuff. Don't do that. I have to write more exams. You can find out what 2016. Here's the spring 2021. What their exam was like. Maybe it'll make you feel better or worse. Here's your equation sheet that you have for the thing. Here you go. Little thing. Right? There's some of them are just multiple choice questions in the beginning. Some other ones. Yeah, here's a collision. Look at that. Little collision. Collision problem. If you don't want to do it, never mind. Just figured tell you the resources. And I wanted to show you her, the happy hovercraft lady. And you saw this in class. It was $729. Worst part, doesn't come with a leaf blower.
just use Bernoulli's principle. Yeah. Yeah.
That's the answer to everything. You already heard that's the answer? My answer? That was my ongoing joke?
No, I just.
This really ruined my ongoing joke? It's not that funny, isn't it? Okay, cool. It's like one of those things I ask all the, a lot of times the FBD is the answer. I just answer FBD all the time. You get a good chance to be right. Yeah. A couple more of those. Oh, apples to apples. We should make my ME 370 class. Someone's always apples to apples. That's the answer to the question. Like, why are we doing this? Apples to apples. All right, so that's it for me, man. I am so tired. I would totally do more problems for you, but I think I get them all wrong. We talked a lot about a lot of stuff that wasn't useful, and it's all been recorded.
It was fun. Say some things you really don't like.
Maybe this lady will reach out and contact me and say that she's a miserable.
I'm about to spend like $2,000 on some marijuana stuff because I just got the criminal.